Hello everyone and welcome back again to the linear algebra component of the calculus and linear algebra series. In the last video we started to introduce this idea of kind of various proof techniques that we can use to prove certain mathematical statements within a mathematical structure. And more specifically what we did is we introduced this idea of a direct proof. So that was a proof that was constructed by not modifying the original statement in any way. We didn't write it in some sort of equivalent form, we just proved it directly, hence the name direct proof. And in this video, we're going to look at another type of direct proof, perhaps probably the kind of crudest form of proof, which is otherwise known as a proof by exhaustion. And that isn't to mean that this is a proof that is constructed where you're kind of lying on the floor exhausted by the end of it, but in some ways it could be. But it is to be thought of as a proof by exhaustion is that you're exhausting all the possible cases that can be considered within that statement. So a statement might have something that can be split up into a finite number of cases that can be checked. And if you check all those cases and check that that statement is valid for all those cases, then you will have proven the statement. But note here that you have to be very careful because there's very few statements that can actually be proven in this way. For example, if I have statements that tell me that I have to prove something for every value of x, and I can't split that value of x over kind of a finitely many subcases, then it is not enough to just prove a couple of cases. So if I have a statement that says it's true for every x and I prove that it's true for, say, 5 values of x, it doesn't follow that I've proven it for every value. And this is a common mistake that's often seen among students, that proving a statement or showing that a statement is true for a couple of cases is not the same as proving a statement for all cases. But a proof by exhaustion is an example or a case where we can actually prove a particular statement by considering only a finite number of cases. If there's an infinite number of cases to consider, though, we cannot use a proof by exhaustion, or we literally would be keeling over on the floor, collapsed, because we would have to wait an infinite amount of time to prove all those things. So let's look at an example here of a proof by exhaustion. So the first one I've got to, that I'm going to consider here is actually one that contains a universal quantifier. So we have here all square numbers are either a multiple of 4 or one more than 4. And you'd say, okay, well, we can't use a proof by exhaustion here because we're considering all square numbers and there's infinitely many of them. So hopeless. But what we can do is we can realize that all square numbers are just squares of integers. And all integers can be split up into two subcases, namely even numbers and odd numbers. So because we can do that, we can use a proof by exhaustion because we consider the cases that we have that all the positive integers must be either even or odd, and therefore we can consider the case where it's even, square it and prove that it satisfies our condition, and that it's odd, or when it's odd, that square it and prove that it satisfies our condition. So let's look at the first case. We're going to consider when n is odd. So if we've got n is odd, then it must follow that n is equal to 2k plus 1 for some k in z, or in the integers. And that just follows right from the fact that that's just the definition of what it means to be an odd number. It's one away from an even number. So now let's square that and see what we get. So if we square n squared, we're going to get this number here. And it results immediately by looking at that n squared is a multiple of 1 more than 4. So we see here that by squaring an odd number, we get this 4 times k squared plus k plus 1. And we see that that's a multiple of 4 plus 1, which is exactly what we wanted to check as one of our cases above in the theorem, right? All square numbers are either a multiple of 4 or 1 more than 4. So we've shown that when we have an odd number and we square it, that we get a number 1 more than 4. So what about when it's even? Now this one's a bit easier. So we have that when it's even, we can take that an even number is 2 times by L for some L in the integers. If we square that, we immediately see that we're going to get m squared is 4L squared, which means that m squared is a multiple of 4, which is exactly our other case. And because we've considered all possible cases now, we've exhausted all cases, that is m is even and m is odd, we've proven that, right? We've shown now that that's done, so we've got our square box at the end to say that this is proven. So this is an example of a proof by exhaustion that actually we've applied to a kind of statement that actually contained a universal quantifier, but notice that we were only able to use a proof by exhaustion because of the fact that we were able to split it up into a finite number of cases. So other examples where I could take a proof by exhaustion could be some theorems or propositions where I say, oh, this statement is true for the numbers between 1 and 5 that are integers, right? And I would just check all the numbers. I could check 1, 2, 3, 4, and 5. I would check them all individually, check that that statement is true, and that would be an example of a proof by exhaustion. But very rarely I would say that proof by exhaustions appear. They're kind of, I would say, the kind of last resort that you should go to when trying to prove things. In general, try and prove it kind of more generally, and then see if it can be proved in an exhaustive way at the end, if you suspect that it's true. So that's where we're going to conclude that bit for the direct proof. And now what we're going to do is we're going to move to this idea of a counterexample. Now, this is a bit of a kind of outlier because it is not an example of a proof. When we generally use the word proof, we generally mean that we're proving things are true. But counterexamples are things that are constructed to show that particular claims, if I claim something to be true, is in fact false. So let's look at some examples of that here, some counterexample examples. A lot of the word examples there. And again, the word example. So it's claimed that the proposition all prime numbers are odd is true. So someone comes to you on the street and for some reason he's asking you this question, are all prime numbers odd? Or I claim to you that all prime numbers are odd. And you suspect that this thing is not necessarily true, right? You suspect that this claim is false. How would you check that that thing is false? You would check that it's false and you would prove to them that it is false by coming up with a counterexample. You'd find an example of something that doesn't satisfy that property, and therefore it must be that that statement is false. So that is effectively all a counterexample is. If you've given a statement that is kind of claimed to be true, you should first, or a statement in general, you should check whether or not it's true or false initially by trying to kind of probe it and put in some cases first and see if you can break it. See if you can find some counterexamples. If you can't find any counterexamples, then you should go on to try proving it. But in general, your kind of philosophy should be that you're very doubtful in mathematics. Any statements you're given, you should generally think that they're false, try and prove that they're false by finding counterexamples, or try and show that they're false, not really use the word prove. And then if it is, you can't find any counterexamples, then you should try and continue to try and prove it. So for this one, we can formalize that statement using our first order logic language. So we've got here that this can be written in this way, and we write all our predicates out as always. So we've got here, for every x in the naturals, p of x implies q of x. Here we say p of x is the predicate x is prime, and q of x is the predicate x is odd. So that's saying that if we've got the case when x is prime, then it necessarily must be odd. So if we can find a single counterexample, so a single value of x can be found such that this is false, then the original statement was false, it wasn't true. So what is a value for which this is the case? Well, this is the case for the number 2, because you might actually think that this thing is true, but if you look, well, number 2 is an example of a number that is prime, but it is not odd. And therefore, I've got here on my kind of implication sign, I've got a truth on the left-hand side. P of x is true for that value of x, but q of x is false. So I've got truth implies false, so the overall thing is false. And therefore, the number 2 is a counterexample to this proposition, and hence the original proposition is actually false. It isn't true. So we found something that kind of does not verify or shows that this proposition must be false because we found a counterexample. And that's generally how all counterexamples will go. So let's look at another example here of a counterexample. Before I kind of move on to that, maybe I should say that generally when we talk about counterexamples to statements, we generally talk about counterexamples of statements that contain universal quantifiers or existential quantifiers. In this example, we see that our statement contained a universal quantifier, and therefore to find a counterexample to this statement, what we did is we show that there exists an element such that the predicate was false, right? That's how we showed a counterexample. And similarly, we'll look at another example here where we've got an existential statement. So we've got one that says something like, it is claimed that the proposition there exists a unique real number x such that x squared equals 2 is true. Now, because we've got the word there exists a unique, how would we show that a counterexample to this? Well, a counterexample to this, we could show that there are 2 values, there are more than one value, and they're distinct values that satisfy this condition. So if we can find 2 values of x that are distinct, then that satisfy this condition, then this statement must be false because therefore it wasn't unique. And obviously 2 values that satisfy that is the square root of 2 and minus the square root of 2. Because if I square those things, then the square root of 2 squared is 2 and minus the square root of 2 squared is also 2. So we've found 2 distinct values because the square root of 2 does not equal minus the square root of 2. And they both satisfy that condition. Therefore, this statement was not true. So we only really talk about counterexamples in the context of statements that generally contain universal quantifiers or existential quantifiers. If it contains a universal quantifier, we show the counterexample by showing there exists an element for which that statement is false, and by showing the counterexample to an existential quantifier, we can show that there are two distinct values for which that statement is false, and therefore it wasn't unique. So that's where we're going to conclude this video now. We finished off now what we're talking about, at least this part of direct proofs. And the next type of kind of direct proofs we're going to talk about is applying that to use something called proofs by induction. And you've probably already seen these before in the calculus component, and you may have even seen them at A level. But we're going to talk about them in more detail on why we can construct them, and in fact, what type of predicates or what type of statements can we use a proof by induction for. We actually see that it's quite delicate. We require a certain number system to work over. And even further, we'll also split our proof by induction up into two cases, known as a weak proof by induction, which is probably the most common one that you've seen, and the kind of less common one, but in fact equivalent, is called a strong proof by induction. So that's what we'll look at in the next two videos, and then we'll start moving on to indirect proofs. So once again, I remind you to look at the notes on the Moodle page and attempt any problems in the module handbook related to this video. So thanks very much for watching, and see you in the next one.